Hello, my dear future makers. Welcome to ACE Engineering Academy. This is Vamshi Krishna, faculty of Discrete Mathematical Structures. My dear students, in this session, we can discuss latest GATE 2022 questions with the detailed solution from our Discrete Mathematical Structures, my dear. So, without wasting the time, let's have a look. Yes, students, if you see subject-wise weightage, so we have many subjects in our computer science. So if we see our subject like discrete mathematical structures, so the subject weightage this year in 2022 GATE, we got 13 marks from this subject. And if you analyze the questions, so we have questions like 3 questions from 1 mark and 5 questions from 2 mark and total 8 questions from our discrete mathematical structures. See this first question, students. Which of the following statement is are true for a group? This is the question from group theory, right? Yeah, you know about algebraic structures. When the algebraic structure is called group, we know that if the given algebraic structure follows the 4 properties like closure, associative, identity, and inverse, then we can call that algebraic structure as a group. So from that concept, they framed the question like this. Option A is for every x and y, xy whole square is equals to x square into y square. Students, don't think here x square y square means x square into y square. There is some binary operation. It may be x square star y square or x square boolean sum y square, x square circle y square, something like that. That is the meaning of that. And then G is commutative. That is first statement. And the second statement is for every x belongs to G and x square is equals to 1. Here also same discussion. X square means x star x. So that is one. Then G is commutative and here 1 is the identity element. They clearly specified that. And coming to option C, the option C says that if the order of G is 2, then G is commutative, order, cardinality. And D is if G is commutative, then subgroup of G need not to be commutative. So there are different statements, my dear. Let us analyze one by one. Yes. Sir, if you see the first statement, for all x comma y, xy whole square is equals to x square y square. I want to take this statement. Sir, here I am discussing option A. Xy whole square is equals to x square y square like. Let us apply operation xy whole square means I can take it as xy is equals to x square xx y square y star y like. Students, understand the given question. If this follows something like xy whole square is equals to x square y square, then it is commutative. When you read this word commutative, there should be something in your mind like for all AB must be equals to BA, right? So our target is something like xy is equals to yx, that is our target. So here I think xy is equals to yx, we cannot prove. But if you observe the question, if you focus on this area, this will be familiar, right? Yx, xy you can take. Yes, we can prove that yx is equals to xy. So the problem with this x and y, so let us operate in this way. I want to operate with x inverse left side and y inverse right side. Am I clear? Yeah, I can balance the step by taking both ways. Don't worry about that. Sir, the above statement is something like xy, which is equals to xx, yy like. Fine, I am operating in this way. So x inverse here, y inverse here. To balance this, x inverse here and y inverse here. Then x inverse star x inverse is nothing but identity. And here also this becomes identity here and here. Finally, I got something like this part, yx is equals to xy. Yes, sir, when xy is equals to yx, then you can confirm that the given algebraic structure, it is already grouped and it can be commutative also. Fine. So option A will be true, my dear. In this way, you can prove A. And let us focus on something called B. Yeah, see this B. For every x belongs to G, x square is equals to 1. X square is equals to 1 means I want to take in this way. X square is equals to 1. It means x star x is equals to 1. It appears like something like A star A is equals to 1. And in the question, it is clearly mentioned that 1 is identity. Right? A star B is equals to identity. If A star B is equals to identity, you know very well A and B are inverses to each other. In the same way, X star X is equals to identity, which means that X is inverse to itself, right? And moreover, we are very lucky it is given in the question for all X. In the given algebraic structure like G, x star x is equals to identity for every x if it is possible. If every element is inverse to itself, then it will be definitely commutative. By famous property we have, if every element is inverse to itself, it will be commutative. So option B is also true, my dear. Got it? And coming to option C says that if the order of G is 2. Sir, here I want to discuss option C. The order of G, order is nothing but cardinality. N of G, there are two elements in the given algebraic structure. And moreover, the speciality of number 2 is that 2 is nothing but a prime number. Yeah, it may be even prime or whatever it is a prime number. So now we have a property. Remember the property. Every group of prime order is going to be commutative. Every group of prime order is an abelian. Yes, sir. This is prime number. So it is also abelian. And C is also true. So up to now what I discussed, the statements A, B, C, all three are true. Now I want to enter into option D. What is this statement talks about? Sir, G is commutative, then subgroup of G need not to be commutative. How, sir? How it is possible? It is not at all possible. Let us discuss. I want to discuss option D here. Sir, there is something like G, group is here. So let us take some elements like A, B or X, Y in this group. Sir, you are talking about something called subgroup. Let us take some subgroup H to this, right? And I want to, subgroup is nothing but a subset, right? So I want to consider some subset H. That H consists the elements like X, Y. Now what I want to say is, I can say in this way, H is need not to be commutative, so I can come into what you called reverse way, right? I can go for reverse engineering, contradiction approach. Sir, for example, if H is not a subgroup, let us suppose H is not need not to be commutative. Subgroup of G need not to be commutative means, let us suppose H is not commutative. If H is not commutative, there exists some pair like X comma Y in H such that X star Y is not equals to Y star X. X star Y is equals to, I just supposed, man, I just supposed H is not a subgroup. There exist two non-commutative elements like X, Y such that X star Y is not equals to Y star X. If it is true, immediately I can say something like this. These two elements, X comma Y they are also the elements of G. Because H is a subgroup, it means that H is a subset. All elements of H must present in G. So immediately these XY are also present in G. In G, for two elements, if this thing is happen, G cannot be commutative. G cannot be commutative, my dear. If H is not commutative, if subgroup H is not commutative, G cannot be commutative. So by using this contradiction, we can say like The option D cannot be answer. That cannot be the true statement. So A, B, C are the true statements to this question. Yes, students, see this question. Consider a simple undirected graph of 10 vertices. There are 10 vertices here. So if the graph is disconnected, then the maximum number of edges it can have. Yes, students. So this is the question from our graph theory concept and about connectivity like. So there are 10 vertices. We have 10 vertices here. 10 vertices, and we want to find out the maximum number of edges. So you can take, sir, maximum number of edges that we can give in our disconnected graph means, in disconnected, the graph is disconnected, we need to take maximum number of edges. That is possible if and only if you have two components, then only it is possible, right? So you can separate one vertex, 9 vertices here and 1 vertex here, just like isolated vertex. And from these 9 vertices, how many edges are possible? Maximum number of edges, 9C2, and the answer is 36. And this is one way of solving the question. And the same question you can solve with a direct formula. The number of edges E is equals to n minus k into n minus k plus 1 by 2. N refers to number of vertices minus number of vertices, I think it is 10. Yes, 10 minus components, na? 2. 10 minus 2 plus 1 by 2, and it will be 8, 9, 2, 4, max 36 possible. Fine. Yes, students, this is the question from our combinator X. The number of arrangements of 6 identical balls in 3 identical bins. Yes, here we have the number of arrangements we want to find for 6 balls. And the speciality of the question is you are taking 3 identical bins, that 3 identical bins or boxes, they are identical, that is speciality, right? So let me take 3 bins like this. Then you should think in such a way that how many ways you can distribute these 6 balls, right? Yes, I think we can take 0 ball here, and remaining 6 balls can be distributed like 1 and 5, and you can also distribute in this way 2, 4, and we can also distribute like 3, 3, and you can also distribute all 6 balls here. Am I right? And after that, coming to the 0 case, I can go for 1 here. If I take 1, then 6 minus 1, remaining 5 balls need to be distributed. So I can distribute 5 balls something like this. If I write 105, it appears to be first case. That's why I'm not writing that. I can take something like this. 1, 4 is 5, and 2, 3, isn't it? And in the same way, I can take all 2's like. Got it? Then if you observe the number of cases, and the number of cases like 1, 2, 3, 4, 5, 6, 7, total 7 number of arrangements possible. Yes, students, this is the question from our generating functions concept. So which one of the following is the closure form of the generating function of the sequence an defined below? And here the sequence an is n plus 1 when n is odd, and same an is 1 otherwise, right? Yeah, let us discuss this. Yeah, students, we have an, the sequence is an. From this sequence, I want to take the generating function. My generating function is the summation of an into x power n, and this an value is n plus 1 when n is odd and the same an value is 1 otherwise, isn't it? Now let us expand this. Here we have summation of n into x power n when odd case and 1 into x power n odd case. I just expanded this, and here otherwise case. Fine. Now n into x power n. Let us elaborate this. Here we have 1 into x power n, 3x power 3, 5x cube, 5x power 5, plus so on like. And the second term is also odd case. So we should take x power 1, x power 3, x power 5 like this. And next I want to take otherwise case, x power 0, x power 2, x power 4 in this way. Fine. Sir, here we have the first term. The first term is like x, 3x cube, 5x power 5, right? And x power 0 x. Let us combine these two terms. We can go for some simplification, right? X power 0 na 1 x, x square, x cube. There is a plus symbol. I just combine these two. That's it. Right? Sir, if you combine this, what benefit you? It is in GP, my dear. Now it is in GP. I can apply sum of infinite terms formula. Right? It is sum of infinite 1 by 1 minus r. A by 1 minus r, just like that. 1 by 1 minus x. Isn't it? Now here I want to check the options like. So I reached something like my answer is x into x plus 3x cube plus 5x power 5 plus so on like, and the second part is 1 by 1 minus x. Isn't it? 1 by 1 minus x. And the first part as it is I have taken. Now here, even in examination also you can stop the question and here you can analyze. The second part is safe. You already got this 1 by 1 minus x. So you need to analyze only the first part, right? If you see the options, in the options we have something like 1 minus x square. Sir, this is 1 minus x square. 1 minus x square whole power 2, 1 minus x square whole power 2. Something we have. Then think about 1 minus x whole power 2 whole power minus 2 expansion. That will help you. What I am saying is, if you see the options, immediately there is a chance your mind can trigger about the expansions, right? It is not a clear expansion. You need to convert that. That is the thing I am saying. Yes, sir. 1 minus x whole power minus 2. The expansion will be 1 plus 2x plus 3x square plus 4x cube like this. Then I have x square in the options. Let us see, if I put x is equals to x square, what I will get? 1 minus x square whole power minus 2. That will be, in place of x, I am taking x square, 1 plus 2x square, 3x power 4 plus 4x power 6. In this way, my dear. And after this, I reached up to here 1 plus 2x square, 3x power 4. Actual my requirement is like this, x into 3x cube. So x I required, I need to multiply definitely with x. X is minimum. But 3 minus x square, I am not sure. Let me try the first option with 1 plus x square. Let us see what's going to be happen. Sir, if you multiply with x into 1 plus x square like, then 1 minus x square whole power minus 2 like in this way, then what do you get? Sir, this part x into 1 plus x square is nothing but x plus x cube, and the second area 1 minus x square whole power minus 2, this is there here, 1 plus 2x square, 3x power 4, 4x power 6. Now let's multiply, you will get something. Yes, x into 1, that is simply x. Don't forget your target, right? X here, and what do you say? X into 2x square is 2x cube. 2x cube plus x cube, 3x cube, isn't it? X into 3x power 4, 3x cube, 3x power 5. X into 3x power 4 become as 3x power 5. 3x power 5 into, if you multiply these two terms, you will get 2x power 5. 3x power 5, 2x power 5. It will become 5x power 5. In this way, you will get the same expansion, my dear. It means that if you simplify this, the second part is already safe. Second part is already safe. And the first part is something like this. If you take this one into the denominator, you will get x into 1 plus x square divided by 1 minus x square whole power minus 2. And the second part same. Means option A will be the answer, my dear. I hope you already taken this is as minus, this is not plus. Fine. A will be the correct answer. Got it? Yeah, questions. Yeah, students, see this 2 marks question from our graph theory. Consider a simple, undirected, unweighted graph with at least 3 vertices. Sir, at least 3 vertices. If A is the adjacency matrix of the graph, then the number of 3 cycles in the graph, 3 cycles, that means the length of the cycle is 3. They clearly specified this. So, in the graph is given by the trace of the matrix here, that A cube, that is nothing but adjacency matrix. Trace of A cube or trace of A cube divided by 2, trace of A cube divided by 3, trace of A cube divided by 6. That is question, my dear. Yes, sir. Here we can take the minimum number of vertices is 3. So you can take 3 or 4, no problem at all. So I want to take 4 vertices to elaborate this question. So let me take 4 vertices. I want to take what do you call K4, A to all, B to all, C to all like, right? So from this K4, we know very clearly the number of 3 cycles, possible is 3. 3 or 4, how many possible? Right? Yeah, 4 I think. Yes, in this way 1, 2, like in the same way here also 2. So 2, 2 more like this. So total 4 cycles are possible. Now analyze the same thing with adjacency matrix. Now I want to take adjacency matrix. Adjacency matrix A is with vertices like A, B, C, D. I am taking number of nodes 4 na, so I am taking 4 by 4 matrix. Right? A to A 0, 0, right? 0, 1, 1, 1 like. Then it is 1, 0. Here it will be and 1, 1, 1, 0. This is adjacency matrix, my dear. Now I want to take A square because in the options I have A cube, right? So I am taking A cube 1 by 1. So I want to take A square first. So 0, 1, 1 like 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, right? And here in this area 0, and 1 0, 1 1 0, 1 1 1 0 like. Is it fine? Let us take a square now. A square is like this. In this way, if you take, so here I got something like 3, 3 na? Yes, 3. Then 0 here, and second element is also 0. Last 1 plus 1, I think it becomes 2. So 3, 2, 2 I have. Then it will be 2, 3, 2, 2 like. Then it should be 2, 2, 3, 2. I hope you know this. 2, 2, 2, 3. I got a square. After getting a square, I should think about what do you call a cube, my dear? Yes, sir. Let us take a cube here. A cube is, we have 3 double 2 like 2 3 2 2, right? 2 2 2 3. A square into a I want to take. I have a like 0 1 1 1 0 1 1 1 1 0 1 1 1 1 0. A square into a. Then my a cube will be, so 0 2 2 2. I think it will become 6. Now I have 3. 2 becomes 0. 3 plus 2 plus 2 I will get. I think it should be 7. 3 7 7 7 like, and 7 6 7 7 like, and 7 7 6 7 like, and 7 7 7 6 like. Sir, this is your matrix. Sir, if you see the options, you are talking about trace of the matrix and all. So let us think about trace. Here, the trace of the matrix A cube is, so this area 6 plus 6 plus sum of principal diagonal elements, you can say, right? So it is 24, right? So I got 24, that's okay, fine. And if I divide 24 with 2, that cannot be not my answer. 3 also not possible. But if I divide that trace of the matrix A cube with 6, something called some answer 24 I got. 24 by 6, and it will be 4. Only this is the option matched with the given question. So DQ will be the correct answer, my dear. Yeah, students, this is the 2 marks question from our graph theory. So see this. The following simple undirected graph is referred to as Peterson's graph. So Peterson's graph they given with Peterson's graph 10 vertices and 2 C5s, 2 cycles, right? So which of the following statement is are true? So the first statement says that the chromatic number of the graph is 3, and the second statement is the graph has Hamiltonian path. And the third statement is the graph is isomorphic to this Peterson's graph is isomorphic to this. Yeah, both graphs are isomorphic, that is that. And last statement is the size of the largest independent set is given for the given graph is 3. So they are the different statements we have. Let us analyze one by one, my dear. Students, if you observe the given graph, so if you want to take chromatic number, I hope you remember the definition of chromatic number. When you are coloring the graph, the neighboring vertices should not have the same color, isn't it? Yeah, you can use the Powell's approach. By using our Powell's algorithm, you can take highest degree vertex and everything. That is fine. But if you observe our Peterson's graph, every vertex is of 3 degree. This is 3 degree. Every vertex is of 3 degree. Na? So you can follow any order. That thing is doesn't matter. So if you color the first graph like this red and the second graph something like blue. So and next is red. So C5 you can color like this, my dear. When you do the coloring like this, um, the definitely the chromatic number of the graph is going to be 3. No doubt the statement is correct. And if you want to verify that, I can show in a pictorial form in this way. Yes, three colors are enough to 3 colors are enough to do the proper coloring of the graph. So the chromatic number of the Peterson's graph is 3, my dear. Here I just used 3 colors only in such a way that no two colors have the same, right? No two neighboring vertices have the same color, isn't it? So can I write something like here? The chromatic number of Petersons will be 3. Got it? The first statement is true. That is the point I want to convey, my dear. And next, coming to Hamiltonian path. Yes, there is a Hamiltonian path, no doubt. You cannot make Hamiltonian cycle, but Hamiltonian path is possible. If you start with this vertex, let me take something here. Yeah. First vertex, second vertex, third vertex, fourth vertex, 5, 6, right? 7, 8, 9. You can cover all vertices. But you started at this vertex, you ended at this vertex. There is no cycle. Hamiltonian cycle is not possible, but Hamiltonian path, the path which covers all vertices of the given graph without repetition of any vertex, that is possible, my dear. Hamiltonian path, the first statement is correct and the second one is also correct. And now let's have a look about this third one. The graph is it isomorphic to the given one or not? I think it is definitely isomorphic. I hope you know the rules of isomorphic. So order of the graph, number of vertices and number of edges, size of the graph, degree sequence. We should analyze the two graphs in this way, right? Order of number of vertices, number of edges, and degree sequence, and what do you say? Number of cycles, number of even length cycles, number of odd length cycles. You see in any format that two graphs are going to be isomorphic, no doubt at all. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 vertices. 10 vertices and edges are also same, just like 15 edges, whatever you say in Peterson's, the same number of edges are available here also. And something like degree sequence, so every vertex is of degree 3, 3 regular graph like 3, 3, 3, right? And cycles are also of length of also same. So both graphs are isomorphic in all aspects. If they are not isomorphic, we can show the reason. They are isomorphic actually in all aspects. So it is isomorphic, my dear. So in this third statement is also true. And whereas coming to the fourth one, the size of the largest independent set of the given graph. For the Peterson's graph, the independent set, largest independent set, I think it's not 3. Largest, it can be 4 also. Independent set, the set of vertices or you can say set of edges which are independent, which are not at all neighbors to each other. Let me take something like largest independent set. So you need to take set of vertices. They are independent. No two vertices are of the subset of edges. That means you need to collect the vertices in such a way that they are not at all neighbors. So how many vertices you can collect? So for example, if you consider, I want to take something like this. Yeah, for example, if you take this one as the first vertex, let me suppose something like this. If this is my first vertex in the independent set, so the neighbors of these, this one and this one, not allowed. but you can take this one as second one, no problem. If you choose this one, these neighbors, this one, and this one, not allowed. But you can choose this one, no problem, right? And if you choose this one, this neighbor, this neighbor, this neighbor, not allowed. But you can choose this one. The largest maximal independent set consists 4 vertices, my dear, not 3. I can show the clear picture, don't worry. Yeah, this is the way. This is 1, 2, 3, 4. They are not at all neighbors to anybody, right? They are not at all the elements of the subset of neighbors. So, your MIS, maximal independent set, is largest maximal independent set consists 4, my dear. So, it is not at all 3. So, because of this reason, we can say that option D is wrong. But A, B, C are fine. This is true, and this is true. And this is the way of solving the question, my dear. And these are the questions. And we have 2 more questions also, just like from recurrence relation, and one more question from graph theory. So the 2 questions are already discussed in our algorithm subject. So if you want to watch that video, you can watch it. So that's why I'm not going to that questions again. So these are the detailed solutions of our GATE 2022 computer science questions, my dear, and thank you very much. Thank you very much for watching this. And speciality of this time is they touched mostly combinatorics and graph theory. That's it. From these 2 areas, they given all the questions. That is the speciality of this paper this time. So we didn't get any question from mathematical logic and set theory and algebra. So this type of scenario we never expected. And models we already covered, na? So same models, almost same models and questions we got. But every time we expect a question from math logic and first order logic, but this time we don't have. Anyway, that's the analysis and the detailed solutions of the our GATE 22 paper. Thank you. Thank you very much for watching.